Let's look at using gases with reactions. Now this is the same thing. We can also change liters of gas to moles at STP. Remember, STP is 0 degrees Celsius and 1 atmospheric pressure. So we also remember that 22.4 liters of gas is 1 mole. Let's look at this. We have 6.45 grams of water. Decompose how many liters of oxygen were produced at STP. So this is the equation, so we should know how to write that equation, and then we have to balance it. So what does this mean? Let's look at this. 6.45 grams of water, and how many liters of oxygen will be produced at STP? So we start with grams of water, and we need to go all the way to liters of oxygen. Now nothing is different. This is all the same thing. It means we have to go to the mole of water. The mole of water can only talk to the other mole. You have to go through the mole of oxygen. Then from the mole of oxygen, you go to the liters of oxygen. Now you know how to do one from going grams to water from moles to water. That's from the periodic table. From moles of water to moles of oxygen. Step 2 is from the equation, the balanced equation, and from moles of oxygen to liters of oxygen. We know that one. We've done that before, chapter 10. We just use our conversion factor of 22.4 liters. All right, so let's start with 6.45 grams of water. 1 mole of water is 18.02 grams of water per. Let's start step 1. Part 2 is from the balanced equation. 2 mole of water, we want to get rid of that, so we put that on the bottom, to 1 mole of O2. Part 3, going from moles of oxygen to liters of oxygen. So we have 1 mole of oxygen. How many we know? That's 22.4 liters of oxygen. So we're left with liters, and we get 4.01 liters of oxygen. How many liters of carbon dioxide STP will be produced from the complete combustion of 23.2 grams of C4H10? We're going to need to write an equation for this. The complete combustion, that means C4H10 plus O2 goes to carbon dioxide and water. Now we have to balance it. Here's the balanced equation. It's some ugly numbers there, but that's what it works out. And we can't reduce it. But so let's start. We have grams of C4H10, and so we have to go to the mole of C4, that's H10. And from the mole of C4H10, we go to the mole of CO2. And then we can get the liters of CO2. First step, get from the periodic table. The second step, always from that equation, moles to moles from the equation. Third step, use that conversion factor, 22.4 liters in 1 mole. So we have to start with 23.2 grams of C4H10, and that's 1 mole per 58.14 grams. Now we go to the mole ratio, and the mole ratio tells us we have 2 moles of C4H10 to 8 moles of CO2. From moles to liters, 1 mole of CO2 is 22.4 liters CO2. We have 35.8 liters of carbon dioxide produced. How many liters of CH4-STP are required to completely react with 17.5 liters of O2? And this is the balanced equation. So we're going from liters of O2 all the way to liters of CH4, and of course we have to go to the mole of O2 to the mole of CH4 to the liters of CH4. And that's first step. 2 mole to mole is from the equation, and that's from the conversion factor. We have 17.5 liters of oxygen. That's what we start with. And we have 1 mole of O2 is 22.4 liters of O2. That's the first step. The second step is from the mole ratio from the equation, 2 moles of O2 to 1 mole of CH4. So these liters of O2 will cancel out. So we have moles of CH4 now, and then from moles of CH4, part 3, we can go to liters of CH4. The moles of CH4 will cancel out, and we're left with liters of CH4, and we're able to figure out liters, we're able to figure out grams. Now we can, of course, figure out particles. So we can change between particles and moles. 6.02 times 10 to the 23rd, Avogadro's number. That could be molecules, atoms, or formula units. Let's look at an example here. If we have 2.8 grams of methane that are burned completely, how many water molecules will be made? So we have to make a balanced equation for that. It's a combustion. So CO2 plus H2O. Here's the balanced equation. Now we can probably, and hopefully you can figure out, how do we get molecules from all this. Now we go from grams. We start with grams of methane. And then of course we go to the mole of methane. And then we go to the mole of water. And from there we go to molecules of water. Grams to moles, part 1, we have periodic table. Part 2, moles CH4 to moles of water. That's, of course, from the equation. Now, moles of water to molecules of water, that is where we use our Avogadro's number, 6.02 times 10 to the 23rd. 2.8 grams of CH4. 1 mole of CH4. 1 mole of CH4 is equal to 16.05 grams. Grams will cancel out. The first part. The second part we get from the mole ratio. We have 1 mole of CH4 to 2 moles of water. Now the third part, going from moles to molecules, we should be able to figure that out. We've done this before. 1 mole of water, how many molecules does that equal? That is 6.02 times 10 to the 23rd molecules. Cancel everything out. We get 2.1 times 10 to the 23rd molecules of water. Now using this same equation, we have CH4 plus oxygen goes to water and carbon dioxide. Now we go from molecules of oxygen. How many are used to burn methane, which is CH4? How many grams of methane will be made? All right, so we're going from molecules or particles of O2. Have to go to the mole of O2 to the mole of methane. And that gives us grams of methane. Okay, so the first thing we can do with that Avogadro's number, the second part we get from the equation, and the third part we can do from the periodic table. We have 1.45 times 10 to the 24 molecules, O2. Now we want to get moles, mole of O2. 1 mole of O2 is, of course, Avogadro's number, 6.02 times 10 to the 23rd. The molecules will cancel out. We're left with moles of O2, so that's the first part. And we want to get the second part, the mole ratio from the equation. And we have 2 mole of O2 And we want methane, 1 mole of a methane. The moles will cancel out. We're left with moles of methane. Now for moles of methane, we have to get grams of methane. So we have 1 mole of methane. And that equals 19.3 grams methane that's produced. Okay, if we have this 6.95 times 10 to the 20 molecules of CH4 are burned completely, how many carbon dioxide molecules will be made? So that means we have to start with the molecules of CH4 must go to the mole of CH4. The mole has to talk to the other mole of CO2, and then we get the molecules of CO2. So going from moles of CH4 to molecules of CH4 to moles of CH4, that's with Avogadro's number. Moles of CH4 to mole of CO2, that's from the equation. Mole of CO2 to molecules of CO2, that is also from Avogadro's number. Let's start with what we're given. 6.95 times 10 to the molecules of CH4, and we want to go to the moles of CH4. So 1 mole of CH4 over 6.02 times 10 to the 23rd molecules of CH4. Those molecules will cancel. Part 2 is the ratio. We have 1 mole CH4 to 1 mole CO2. Those moles will cancel. And then we want molecules of CO2. So in 1 mole of CO2, we have 6.02 times 10 to the 23rd molecule. Right, so we cancel this out, and then we multiply everything across. Now you'll see that all this stuff is the same. It just cancels out. So, of course, the answer is going to be 6.95 times 10 to the 20th molecules of CO2. Now, if the moles are the same, and you're going from particles to particles, you don't even have to calculate anything. And the same thing with liters. You don't have to calculate. Everything is the same number. So if the moles are the same in the equation, and you're going from molecules to molecules, you don't have to calculate anything at all. And the same thing with liters. If you're going from liters to liters, it's going to be the same. So if I had 100 liters of CH4, I'm going to have 100 liters of CO2. So a lot of this you can actually do in your head, but it's just good to practice because usually you're not going to get such a nice number like that. Review, if we start with grams of A, we go to moles of A, we go to moles of B, and then we could go to grams of B. And grams A to moles of B is through the periodic table. Moles A to moles B is through the equation. Moles of B to grams of B is through the periodic table. Now, if we start with liters of A, we go to moles of A, and we can go to liters of B, or we can go to grams of B. Going from liters of A to moles of A is through 22.4, of course. Anytime you go to liters, you have to use 22.4 for moles to liters, 22.4 for particles. We use 6.02 times 10 to the 23rd. You can go from anywhere to anywhere, from particles of A to liters of B. You just follow the arrow, you go through the moles, and you just use the conversion factors that you've known. So everything is really the same as we've done before, but now we just put in an extra little step of going from the moles of one thing to the moles of the other. And this is our ticket. This is our translator. This is what we have to go to. And from there, everything is gravy.